Welcome to 5-Minute Papers on AI for the Planet. I'm Grace Lindsay. Our paper today is Alpha Earth Foundations, an embedding field model for accurate and efficient global mapping from sparse labeled data. Let's get started. Over the past decades, Earth observation scientists have amassed a tremendous amount of data from a combination of aerial flights, satellites, and ground observations. Traditionally, this data has been used in a somewhat piecemeal way. End users will pull the specific imagery or maps that they need for their purpose and build a data analysis pipeline on top of it tailored just to their needs. But what if, instead, we could combine all this data and build from it a single model that could be used by everyone? That is exactly what this work aims to do. Specifically, the authors of this paper create a foundation model for Earth observation data and use it to generate general-purpose embedding fields that can be helpful for many different tasks. As with all foundation models, this model, which the authors call Alpha Earth Foundations, is trained on a lot of data. And in this case, the data comes from many different sources. This includes optical data from the EU's Sentinel-2 and NASA's Landsat 8 and 9 satellites, radar data from Sentinel-1 and Pulsar-2, LiDAR data collected from the International Space Station, and environmental data, including elevation maps, climate and weather descriptions, and gravity field anomalies, which can track water changes. Each data source is scaled to a resolution of 10 meters per pixel, which is the native resolution of the Sentinel-2 satellite. To build the training set for this model, the authors needed to choose a set of locations that represent diverse landscapes, while also emphasizing regions of most interest. To do so, they took into consideration regions that had geocoded text associated with them on Wikipedia. They also ensured that they had locations which were sampled uniformly from different ecoregions as defined in the Resolve Ecoregions dataset. Finally, they used the ALAN Coral Atlas and Global Intertidal Zones dataset to find locations that represent near-shore ecosystems, which are important for many ecological and policy-related use cases. After removing locations that are only open water, they end up with over 5 million samples across the globe. Each location is a 1.28 kilometer squared grid, meaning the whole training set covers a total of over 6 million square kilometers, or about 1% of land surface area on Earth. Data from these sources and locations were organized into temporal sequences, with data spanning several months. In total, nearly 8.5 million sequences were created, constituting over 3 billion individual frames. Each of these sequences is passed in as input to the model. During training, a single frame from each sequence is randomly removed. After going through individual source-specific encoders, the information from all sources is combined, along with a time code, and passes through a structural bottleneck in the network. This creates a condensed and information-rich embedding of the input sequence. Decoders for each data source are trained to take in the embedding and use it to reconstruct that one missing frame. This process ensures that the embedding is trained to contain useful information. To further encourage these embeddings to be information-rich, an additional objective is added that aligns the embedding with text descriptions of the same location from geotagged Wikipedia articles and crowdsourced species labels. To make the embeddings robust to missing data, they are also trained to output the same response even when some input data is artificially removed. With these objectives in place, the model, which contained roughly 480 million parameters, was trained for 56 hours on 512 parallel tensor processing units. Once trained, the model is capable of generating a 64-dimensional embedding that summarizes an entire time period of Earth observation data at any given 10-meter squared location. In the example here, the patterns that describe a year of information about the Krishna Raja Sagara Reservoir in India are visualized. We can see how the model segments this region into different clusters based on their material properties and how they change over time. Given the information they contain, these 64-dimensional embeddings can be used for any number of downstream analyses. And indeed, the authors show just how performant they are on 15 curated example tasks. For each of these tasks, a simple classifier or regressor is trained to map the embeddings to the values of interest. For example, in this case, the embeddings are used to classify which crops are present at what locations. As you can see, Alpha Earth outperforms all other models tested. Because the Alpha Earth embeddings capture a temporal sequence, they can also be used for change detection tasks. Here again, Alpha Earth outperforms other approaches. The authors also explored how performance on these tasks depends on the amount of data used to train the model. While more training data does lead to increased performance, training data alone does not explain Alpha Earth's abilities, as different models trained on similar amounts of data don't achieve the same accuracy. The authors also look into which of their input data sources are most important for the model's performance. To do so, they trained variants of the model with increasing data sources included. In general, more data sources leads to higher performance, but with diminishing returns. To let others explore Alpha Earth embeddings on their own tasks, the authors run the model on all locations across the globe and share the embeddings representing annual summaries for the years 2017 through 2024 on Google Earth Engine. They also make these embeddings memory efficient. By storing them as 8-bit rather than 32-bit numbers, they take up 4 times less space without compromising on performance. Overall, the authors hope that the design of Alpha Earth foundations will provide a broadly useful and stable way of representing Earth observation data, even as individual data sources come and go. That's all for this episode. Remember to subscribe to this channel for more examples of how AI can be used to protect and describe our planet.